Hi, today we'll talk about passage of light through a prism. So when a light ray passes through a prism, two things happens. Because of refraction, the light rays get deflected, as well as if we have a light, it get dispersed into different colors. We are going to deal with dispersion in another video, and today we are going to focus on refraction and deflection. Now, when you have a geometrical optics problem, basically you have two parts. First is about the physics of the problem, and then you need some geometry to solve the problem. Physics is very simple. In case of prism, basically you need to know the law of reflection and law of refraction, which we already covered. Now let's brush up few of the geometrical concepts so that we are able to solve the problems in geometrical optics. We know all this, but just to revise, so whenever we have a triangle, theta 1, theta 2 and theta 3 is going to be equal to 180 degrees. And when we have a quadrilateral, theta 1, theta 2, theta 3 and theta 4 is going to be equal to 360 degrees. Okay, so that was easy. Now here we have a right angle triangle. This is H, this is L, this is 90 degrees and this is theta. You can write tan theta is equal to H by L. Now for very small angles where the theta is very small, like 1, 2, 3, 4, 5 degrees, basically we can assume that tan theta is going to be equal to theta and sin theta is going to be equal to theta. Similarly, cos theta is defined by L divided by L square plus H square, and for a small angles, basically cos theta is going to be 1. You can verify that by looking at the tables of sin, cos and tan theta in a book. Second thing I want to highlight is that sin alpha plus beta is going to be sin alpha cos beta plus cos alpha sin beta. So we are going to use all these identities, formulas and assumption while trying to solve geometrical optical problems. So just to refresh that and keep in mind. So here we go and move on to our first issue. So here we have a general case of ray of light passing through a prism. So this is how it is passing. So this is a prism with an angle of refraction theta, okay, so which is given. The prism has a sort of refractive index and we already know about that. Now the ray of light is going to enter the prism here like this. Now as you know, it is going to enter the prism, so the medium is changing, and so first thing first we need to understand the physics here. So we need to draw our normal, which is this one. So let's draw our normal. Like this, and as it is entering a denser medium, it will bend towards the normal, so the ray will go like this. So let me draw that right. The ray will bend towards the normal, and when it reaches point B here, basically it is going to enter a lighter medium, right? So this is a denser medium, a glass, and this is air. So it is going to enter a lighter medium, so it is going to bend away from the normal. But first thing first, we need to draw our normal. So here we go. So in this case, draw perpendicular to this all the way from here, and this is our normal. And now the light will travel like this, get refracted away from the normal and go like this. So this red line will actually show the path of light, and we know that we can write some equations using Snell's law at the point A and point B, and that is where all the physics will end. Then rest of it is generally geometry, and what we endeavor to find out that if the ray of light was coming like this, how much deviation happens here, which means the ray of light was coming like this, it would have gone like this, okay, and now finally it ended up going like this. So how much this angle is, right? So this delta is angle of deviation. Always remember, a lot of prism problems will ask you to solve for this angle of deviation, and there are a lot of special cases where we observe this in case of small theta and things like that. But this is a very general case, so no, this is light ray which is coming in. Here we have angle of incidence alpha 1 get refracted, so we have this one here, beta 1 hits the interface here. Now it will hit the interface at a certain angle. This is a normal, sorry, this is the normal, so this is going to be another angle of incidence here, right? And then it will get refracted and will come out at angle alpha 2. Okay, so these are all things we know, and we need to find delta. So we are going to write some equations, but before we proceed, some geometry will help us write those equations. Okay, so first thing first, as you can see, let's redraw this triangle here. Something like this. We have this angle is theta, which is known, we know about the prism. Now here is point A, and the light is going to come like that, so we need to draw a normal. So we'll draw a normal perpendicular to it. Okay, so this angle here is going to be 90 degree, and then the ray of light is going to hit somewhere around here, so we'll draw another normal here, again perpendicular to it, this time like this. Now we know from basic geometry that because this is perpendicular, okay, this is 90 degrees and this is 90 degrees. So as we said, in a quadrilateral, basically sum of this plus this plus this and this angle is going to be 360, right? So we don't know this angle, so let's call it angle A. So we'll say A plus 90, moving in this direction, plus theta, and plus 90 is 360. Now this is 180, so A plus theta will be 360 minus 180 equal to 180. Hence, A plus theta is going to be 180, and we know that this is also a straight line, so 180, so this is going to be theta. This is what we have shown here, so this is our theta again. So remember that we can simply prove it by looking at this quadrilateral. Now we are going to write the Snell's law, but before that, as we endeavor to find this angle of deviation, let's see what it is, right? So here this is delta, okay, and delta is nothing but this is the first deviation, right? So the light is coming like this, then it is going to deviate like this, so it is like CAB. So delta is nothing but angle CAB plus, now the light was going like that and then again got deviated, okay, so this angle, so this was the direction, now it is in this direction, okay, so this angle, which is angle CPA. So this is our delta, and this is what we want to find out, that how much the light is going to deviate when incident on the prism and passing through it, right? Now angle CAB, now this is our alpha 1, so by definition this is our alpha 1, and if we sort of minus beta 1 from this, we'll get this angle, right? This is our CAB, so this one is going to be equal to alpha 1 minus beta 1, that is our CAB. How about CBA? again this is alpha 2, which is going to be all the way equal from here, minus beta 2 will get CBA. So this is alpha 2 minus beta 2. So nicely written here, our delta is going to be equal to alpha 1 minus beta 1 plus alpha 2 minus beta 2. So this is a general expression for sort of finding the deviation of the light ray when it is passing through the prism. And now we are going to find and write few more equations to make it simple. So here let's look at theta, okay, because we know theta, so somehow we have to include that in other unknown variables like alpha 1, beta 1, things like that. And if we can find a relationship between the known variable and unknown variables, it will be easier for us to solve and go through the problem. Okay, so now let's look at this triangle only. Okay, so here we have A is something like this. This is B, this is D, this is our theta. Okay, now this one is beta 1 and this one is beta 2, and as we say in a particular triangle, this is going to be 180, right? So beta 1 plus beta 2 plus this unknown angle A is going to be 180. And now we also know that this is a straight line, so theta plus this unknown angle is also going to be 180, right? So A plus theta is also going to be 180, which means that beta 1, let's write it over here, other side. So beta 1 plus beta 2 is equal to theta. So now we have found a relationship between a known variable theta, which is going to be equal to beta 1 plus beta 2. Now that was geometry. So now let's move to the physics and let's write down the Snell's law at point number A. Okay. So Snell's law at point number A is going to be a first equation. So this is the refractive index is 1 into sine of alpha 1 is going to be equal to refractive index inside the prism is n into the angle of deviation refraction, angle of refraction, like this. This is our first equation, sine of alpha 1 take it down, sine of beta 1 is equal to m. Okay, this is our equation number 1. Now we can write the Snell's law at point B, and that will give us our second equation, which is again very simple. So in here it is refractive index n, so sine of beta 2 is going to be 1 into sine of alpha 2. Okay, now we know that beta 2 is actually nothing but theta minus beta 1. Okay, so substitute that, basically you get sine of alpha 2 this side divided by sine of beta 2 is equal to n, or we can say sine of alpha 2 divided by sine of theta minus beta 1 is also equal to n. Okay, so we are trying to write the equation where everything is equal to n. This is our equation number 2. Now just look at this. Let's define the delta again. So this delta in here alpha 1 plus alpha 2 minus beta 1 plus beta 2. Okay, we have shifted the bracket. Put simply, it's alpha 1 plus alpha 2 minus theta, because beta 1 beta 2 is equal to theta. So now we have everything written in alpha 1 alpha 2 alpha 1 and beta 2. Okay, beta 1 beta 2. So sorry, beta 1, right? So we already have a relationship between beta and beta 2. So we have this three equation which formulates the general law here, which we want to write separately so that we can follow it up. Okay, so we have, just write it down so that we can revise as well. Equation number 1, in here it says that sine alpha 1 divided by sine beta 1 is equal to n, and this is also equal to sine of alpha 2 divided by sine of theta minus beta 1, right? And the deviation delta of the ray is nothing but alpha 1 plus alpha 2 minus theta. So this is the equation in general case. Okay, so now if we know theta 1 theta 2, we can find the deviation. Okay, sorry, alpha 1 alpha 2, we can find the deviation, and we can relate all these things through the Snell's law. Now let's look at a different case where we have a ray of light passing through the prism, but it is symmetrical. When I say symmetrical, it means that we draw a sort of line from here, right? Both the sides is same, so the ray is coming like this. It's perpendicular to this normal, and then passing like that, and it is actually parallel to the base. Okay, so let's see what happens in this case. So first thing first, by symmetry, we can say that this alpha 1 is going to be equal to alpha 2, and let's call it alpha. Just bear with me because this is slightly, so alpha 1 is going to be equal to alpha 2, and we are going to call it alpha. Now the delta we know is alpha 1 plus alpha 2 minus theta. We know that this is equal, so in this case it is going to be 2 alpha minus theta, right? So this was our third equation which we wrote here. Delta was alpha 1 plus alpha 2 minus theta, so we just substituted for this particular case, and we have our new delta in this case. Okay, so delta. Now with the symmetry, basically you can also see that this angle here, right? So this angle here is theta by 2. This one is also theta by 2. And this is a perpendicular. Okay, this is a perpendicular. So this is 90. This angle over here is going to be 90 minus theta by 2. Now again, this is also perpendicular. Hence, beta 1 is equal to theta by 2, and by symmetry it is also going to be equal to beta 2. You can try it yourself and you will arrive at the same conclusion. Okay, now using this new expressions, we can rewrite our equations which we derived earlier, and we are going to do it over here. So sine alpha 1, so let's try and write it from the very basics actually. Okay, so let's write the Snell's law at this point. Okay, at this point, which is going to be 1 into sine alpha is going to be n inside the prism, going to be sine beta. Okay, now what is our alpha? So alpha is delta plus theta by 2. From here, substitute that sine of theta plus theta by 2 is going to be equal to n sine of beta. Beta is nothing but theta by 2. So we are interested in the alpha, so we'll do the, sorry, we are interested in delta, which is a deviation here. So delta will be sine inverse of this one. So first let's write down for sine inverse of n sine theta by 2. Okay, and delta is going to be equal to 2. So go that side, 2 into sine inverse of n sine theta by 2, and this theta will come this side, so minus theta. Okay, so this is our deviation in case of symmetrical passage of ray, and we now have a better equation compared to this one where we are trying to solve this. Now the question is that in what case we are going to have this deviation as a minimum, right? So we have this ray of light falling like this here, sorry about that, and we have certain deviation delta. In this case, the ray of light falling symmetrically, and we have this deviation delta, and we can prove that in case of symmetrical falling, actually delta is the minimum. And let's try and do that very quickly. If you do not know calculus, do not worry, just watch the video and do not worry much about that. So we know that our deviation is basically defined by this equation here. Theta is equal to alpha 1, alpha 2, and minus theta. Now, in order to minimize this quantity, we need to differentiate it with respect to something. Okay, so let's say we are going to differentiate it with respect to beta 1, because we already know the equation of alpha 1 as well as alpha 2 with relation to as a function of beta 1, right? So simply we are going to differentiate this with respect to beta 1 and make it equal to 0, right, by the law of calculus, to find the minimum deviation. So for minimum delta, we are going to differentiate with respect to b1. So this is a function of b1, sorry, beta 1. We'll get d of alpha 1 d of beta 1 plus d of alpha 2 and d of beta 2, and theta is constant, so it is going to be 0. Let's set this to 0, and after solving this, we'll arrive a certain number which will tell us the minimum value, right? So we need to find these two expressions here, and then add them up and set it to 0. Okay, so d of alpha 1, d of beta 1. Now what is d of alpha 1 in terms of beta 1? We have it here. Okay, that's like that. Sine of alpha 1 is going to be n sine of beta 1. Alpha 1 is going to be sine inverse of n sine beta 1. So this is alpha 1 is now the function of beta 1. That's what we want. So we are going to differentiate that over here. Sine inverse and sine beta 1. That. And the second one, which is our alpha 2, we can write that here. alpha 2 is going to be sine of alpha 2 and it is sine theta minus theta 1, right? So alpha 2 is going to be sine inverse of n sine theta minus theta. We know we are going to differentiate this two sine inverse functions, and basically we can arrive at summation of that and then make it equal to 0 for it to work. So t alpha 2, right. As I said, if you are not following it completely, it's okay, just watch it, right? Because what is important at that end of the this exercise, what we arrive at, okay? So we are going to write it as sine inverse and sine theta. Now we need to differentiate this inverse function, so let's introduce this formula. So d of dy by dx of a sine inverse function, the form of fx is equal to 1 minus f square x to the power minus 1 by 2 and followed by df by dx. So if you do that, basically you will find that, see, maths is not important here, it is just about that concept, okay? So do not worry much about that. So when you differentiate this expression, the first one here, you find that d of alpha 1 by d of beta 1 is equal to n cos beta 1 divided by square root 1 minus n squared sin square beta 1. And similarly for the second one, d alpha 2 by d beta 1 minus n cos beta minus beta 1. You can try that when you have mastered the differentiation and maximum minimum problems. You will be, this is a very simple maths, you will be able to follow that. But don't worry, it is not going to be asked in the exam, this proof. I'm just doing it so that you have a fundamental clear. Now when you, as we said, we need to sort of is equal to 0. By equating this, we will get the value, and when you do that, basically we'll arrive at the minimum value, something like this. Beta 1 has to be theta by 2. And in that case, we have a minimum deviation. What it means is basically, in case when we have this ray of light in the center is parallel to the base and passing symmetrically, we have a minimum deviation. And that's what you want to remember out of all this exercise, okay? So I'll write it down. In here, when the ray of light passes through the prism, we have minimum deviation in the case of symmetrical passage light. That means while the ray is traveling inside the prism, it is parallel the base. This is important concept, and so we're going to call it our concept. Remember this, and that's all you need to know. Do all the physics, forget about the maths here, right? So I will explain it once again because this is important. This is going to come many times, okay? So here we are. What it says is a very simple thing. So we have a prism here, Okay. Whenever we say the ray of light is passing through it has a minimum deviation, it means that doesn't matter at which angle. Sorry, let's change the color. Which angle of incidence is coming, it has to pass symmetrically through it. Okay. Now this one, okay, this ray of light when passing through it has to be symmetrical, and this one has to be parallel with the base. And that is all this is all about, right? So in that case, you have minimum deviation. Okay. So in this case, when these two rays, sorry, this ray is parallel to the base, okay, we have a minimum deviation. Prove with a lot of calculus. You can try that when you have grip on maths, and you find the same. So this is what it is all about, right? So now we can look at another case where we are trying to pass the ray of light through the prism, and we can simply solve it using simple mathematics. So here we go. So here we have a prism with an angle theta, okay, and now the ray of light is so it has a refractive index n, okay. The ray of light is incident normally on this face. So now let's see with physics what is going to happen. Okay, I think if you just focus on the physics part of it, that's what matters. So as it is getting normally incident here, right, there is no refraction. It will come straight like this. Okay, now it is going to meet here. Whenever there's an interface, first let's draw our normal. So in this case, our normal is perpendicular to the interface, which is this one. Okay, now this one is our angle of incidence. Okay, I will just write that down. Sorry. This one is our angle of incidence, and then from the normal, because it is going from a denser medium to a lighter medium, deviate away from the normal. So finally, the path of light is going to come straight from here away from the normal. Okay, that's very clear, and this is what the whole physics is all about right now, right? So it's going to do not deviate here because coming perpendicular, and then it's going to deviate away from the normal. Now, this was the original path of light, okay? Then it got deviated. So this is basically the deviation we are looking for, right? So in all the prism problem, basically it will ask that how much deviation it is. So this is the deviation we are looking for. Now we know this is our angle of incidence, and by symmetry, basically, basics, this is 90 degree. So this is going to be 90 minus theta. Okay, this is again perpendicular. So this is going to be theta. So in this case, I is going to be theta. It's a simple geometry. And as I said, like a lot of problem in the physics, in the geometrical optics has two parts. You need to know the physics as well as geometry. So this is basic geometry. We can prove that basically the angle of incidence I is equal to theta. Okay, so if this is theta, this thing here is also theta, right? Now this is our angle of refraction, this alpha I, right? We want to know this one, so delta is going to be the alpha dash minus theta, correct? This is what is going to be our deviation in which we are interested in. Now we can simply write the Snell's law here. Here it's the same. So here we'll write the Snell's law at point number P. Index of refraction, sorry, Yeah, inverse of n is means sine of theta, sine of phi, but it is equal to theta. In here, 1 is going towards the air, sine of alpha dash. And theta is going to be equal to, we already have theta, we need to know sine of alpha dash. So this is sine of alpha dash is equal to n sine theta. Alpha dash is going to be sine inverse of n sine theta. Plug this here and we have our delta, which is sine inverse n sine theta minus theta. So we can find the deviation because we know theta, right? So now everything is in form of the known variables. Theta is known and n is known, and if that is known, basically we can find the deviation. So hence the problem is solved. So similarly, always remember that as I said in our previous problem solving exercise as well, that you have to always remember the Snell's law will be valid. You have to figure out that where to apply them, and that's what matters. So all the geometrical optics problem is nothing but part physics and part geometry. If you know exactly how to apply physics, how the ray of light will be traced in an optical system, and then you can use simple geometry to solve all the problem.